Okay, so in this video, we are going to go over some of the main concepts of thermodynamics, including the basic equation of statics for ideal gas, and we're going to derive the formula for a differential volume given a certain system, and then we are going to eventually make an expression relating the density in terms of pressure and temperature. So this is kind of just the first step. There's going to be 3 parts to this problem, and I'm just going to go ahead and start by explaining our differential volume of a fluid. So let's say we have this fluid here, and then in the fluid we're just going to extract, blow up a small portion of the fluid. So I'm just going to make it a cube, and so this is our differential volume. Apologies for my 3D skills, but this is essentially what's going to represent our differential volume for the fluid, and this is going to have a certain height and a certain area. So this part up here, we're just going to call it A. That's going to be the area. It's going to have this differential. The Z represents position. So a very small position, and then this down here, if this is Z and this is dZ, up here we will have dZ plus Z to represent the position of our fluid. And so we know that this direction is positive just based on the way we drew it. So this is just essentially our differential height here, like that. Okay? And so now what we want to do is we want to establish an acceleration or a velocity for this system, because we have this fluid, and so we know our acceleration is going to be 0. So when we have 0 acceleration, it means constant velocity. And that'll become important later when we do the energy balance equation. So this volume is surrounded by fluid, and it's moving at a constant velocity, which equals 0 acceleration. So then this is important because now we know that if our acceleration equals 0, then when we write our force balance equation, we will have the F equals ma, and our acceleration is 0, so our forces must be 0. So now I'm going to redraw this cube and show the forces on it. So when we have our fluid like this, we're going to have a force pushing down on our fluid and a force pushing up on this area here, just like that. And the forces cancel each other out because we know force equals 0. We also have our force of gravity, which is always acting down, represented by G. So G equals acceleration due to gravity acting down on our fluid. And then we can also, since we know that this is a fluid, a force on a fluid, we can represent that in terms of pressure and area. So we can write force on fluid equals pressure and area. So this force here, down here, we have the area, remember, multiplied by our pressure, and this is position Z. So pressure at Z. We have that there. And then up here we have the same thing, area times pressure, but it's going to be our dZ plus Z. Like that. Okay, multiplied by our area. And remember, this is just a sample of the whole fluid. We're blowing up a small portion, a differential fluid, to represent to derive the equation of statics for an ideal gas. So essentially what we're going to do here is represent the sum of all of our forces with an ideal gas, and so the small change in pressure is with respect to a small change in height, which is what we do. We have our differential pressures and our dz. So I'm just going to write that here. We have a small change in pressure with respect okay, I'll go over here now. So now we need to sum up all of our forces. I'm just going to write, this is just the sum of the forces is going to be equal to, we have our force here, PZA, and then this force is negative because it's acting down, minus PZ plus TZA, and then we also have our force of gravity, which is represented within the mass of the fluid times gravity equals 0. Okay, so now that we have this, we can rearrange it and represent it in different variables that we want. So we don't want, we want to be able to have the density in there, and we want to get rid of the volume. So I'm going to move things to the other side, and we're going to end up with the negative area times, we can factor out the area, we have PZ dz plus z minus pz equals mg, like that. And then we know from our density formula that mass equals density times volume, so we can plug that in and we end up with that, and then we can substitute in for volume. We know that the volume, we can find the volume of this cube by doing the area times the height. So we have our A times dz, like that. We have our area times our height, and then we can substitute that in for the volume. And then what we're going to get is an expression relating the density to just the pressures, because we're going to divide by our pressure, our differential position over here, so that we have things on separate sides. So we end up, and canceling the area, so we'll end up with something with just pressure and position. So we get P dz plus C minus like that, right? Oh, and we have our negative over here because it was a negative area that we divided by. So now that we have this, what we're going to do is use the ideal gas law to get rid of the density and the gas constant, or sorry, just the density, and move some more things around. I'm going to erase this over here. It's not erasing. Okay, so let me just write our ideal gas law so we know where we're going with this. We have our PV equals nRT. So then what we can do is we can use this, and our density equals mass over volume, and this formula down here, and we're going to rearrange this equation. So we now have the number of moles divided by volume equals pressure over RT, like that. And we have our density equals our mass over volume, so we can now substitute, and we know that density equals P times our mass divided by RT. Okay? So now we have everything we need. We have this and this. Put them together. We get our differential pressure divided by our change in pressure compared to our small change in position equals negative pressure times mass over RT. Oh, and yeah, our gas constant. Okay, so hopefully that makes sense. And now that we have this, we're going to use, this is our first equation that we'll have for our equation of statics that we're going to use in this video, and the next equation we're going to derive from the first law of thermodynamics for an adiabatic reversible process. That's the first step. Okay, so now we're going to move on to part two. Part two includes, we're going to make a relationship, or we're going to derive an expression that relates temperature and pressure, and we're going to do it for an adiabatic reversible process, which is essentially just a process in thermodynamics where there is no heat transfer. So I'm going to write the first law of thermodynamics, and then you'll see how it all applies. So we're going to start with the first law of thermodynamics, and then we're going to derive our expression. And in order to visualize this process, we're going to think about it in terms of pockets of air. So essentially, let's say there's a pocket of air, and then like this, 1 and 2, and as this air rises, it expands. So this is what we're going to use for our expression. This is essentially going to be position 1 and position 2. And we have a change in height, and we'll have a change in pressure, which we will see. So for the first law of thermodynamics, we have du plus dq equals p in internal energy. Our differential change U represents internal energy, dq change in heat, and then our pressure and our change, I forgot my D, it's supposed to be change in volume, not just volume. Okay, and so we know for an adiabatic process there is no heat transfer, so in this equation we have dq equal to 0 because we're talking about it adiabatically, and we also want to make sure that we account for the reversible part, and so that essentially just means that the pressure inside these little air pockets is going to be same as the pressure outside. So that means that it's an adiabatic reversible expansion. dq is 0, and we have, I'll write it over here, pressure inside equals pressure outside. Okay, so now we've accounted for the adiabatic reversible part, and we're going to go ahead and use our first law of thermodynamics. I'll just rewrite it now that we know that dq is 0. We have du equals negative p dv. So this is where we're going to start, and we want to relate it to the ideal gas because that's what we did for the last video, or the last problem. So then we can use the two equations together, so we want to make sure that we relate as ideal gas. Like that. And so we're going to note that since dq is 0 and since this is an adiabatic, our change in internal energy here, this du is only due to pressure, or to temperature. So that's how we're going to relate our pressure and temperature, because we know that since there's no heat transfer, it's an adiabatic reversible process, our change in internal energy is only affected by a change in temperature. So then we can rewrite this using what we know about temperature and specific heat and our ideal gas law and make our equation. So over here I will just write, we have our du, our change in internal energy, is related to CV dt. This is specific heat, and this is our change in temperature. And then we also have our pressure equals RT over V. Because we're accounting, because the number of moles we're just going to say is 1. So PV equals nRT becomes P equals RT over V. So now what we can do is we can put these two equations together, and so we get, right? So we have our CV dt equals negative RT over V dV. And then what we want to do is we want to be able to integrate this so we don't have our differentials on either side. And so what we're going to do is bring the t to the other side so that we can integrate. So bring temp to other side. And what we're left with is CV dt over t equals negative r over v dv. Right, so now that we have this separated, I'm actually going to write this, since r is just a constant, I'm going to write it as negative r dv over v, just so it makes more sense when we integrate it. So we'll put our little integration things in here, woo, woo. And then, this doesn't look very good, we're going to integrate it based on our picture over here. So essentially, you know, we'll have our temperature at 1, temperature at 2, volume 1, volume 2. So those are going to be our limits of integration. Make this in a different color. Like that. So then when we integrate this, we will end up getting natural logs on both sides. So we're going to end up with something that looks like CV, since it's just constant, it's on the outside, natural log of, and so the limits of integration you subtract, and when you subtract natural logs, one of the properties of natural logs is then you can make it 1 by dividing them. So T2 for T1, and then we'll have the same thing for the other side, equals negative R natural log of V2 over V1. Okay? So then we want to be able to get rid of these natural logs, so we have to move some more things around. So what I'm going to do is move the CV to the other side, and then you can use another property of logs, which is raising it into the exponent of the log, and then when you do, you know, e to the natural log, it will cancel both of them. So what we're left with, I'll write multiply by CV properties of logs. So then what we're going to be left with is our T2 over T1 equals V2 over V1, all raised to the negative R over CV. Okay? So this is what we have. We used our properties of logs to simplify, and now what we want to do is, in our last equation, if you remember, we didn't have any volume, so we want to get rid of the volume so that we can relate it to the first equation. So we're going to go back to our ideal gas here, and I'm actually going to erase to make some more space. So we're going to go back to our ideal gas here. We have our volume equals RT over P, just like that. So this is just from our ideal gas law, and we're going to substitute that into here. When we do that, we will have our temperature times the pressure because we have the inverse of this. When you substitute it into the equation, it flips it. And so just like with our temperature and volume, we have, a pressure at 0.1 and a pressure at 0.2. So we can substitute this in, and we end up with T2 over T1 is going to be equal to 2 times P1 over T1 times P2, all raised to the negative R CV. Okay, so this is what we have for this, and essentially all I did was multiply by reciprocal so that we can simplify this even further. And what we want to do is when we multiply by this reciprocal, then it's going to change. We want to change the power up here, or we want to separate the temperatures and the pressures, and so in order to do that, we're multiplying this by the reciprocal, which is going to add a power over here. So essentially we're going to get T2 over T1 times, because we're multiplying by the reciprocal of this, P2 okay. So this is what we end up with. Yeah, just making sure I did everything right. And so then we want to combine this fraction and do a couple last minute simplifications. So we get T2 for T1 all raised to the CV plus R over CV equals P1 over P2 raised to the negative R over CV. And essentially we're almost done. We just want to get rid of the power on our temperature. So we're going to multiply by the reciprocal of this to get just the temperature, T2 over T1 equals our pressure with the power. So we'll have, in the end, our final equation is going to be T2 over T1 equals P1 over P2 all raised, right, because we're multiplying by the reciprocal of that to get rid of the exponent. Okay, so that is our expression relating temperature and pressure for an adiabatic reversible process. Now, we started with the first law of thermodynamics, and we have our little air system over here. So now that we have this and our first equation, we're going to go back, put them together, and integrate in order to finish up this problem. Okay, so this is the last step in this problem, is we want to use our two equations from the first two parts to make a expression relating pressure and altitude, and temperature and altitude, or essentially the position and altitude are the same thing. So what we're going to do is we're going to substitute the equation we got from the second video into the first equation, and we're going to simplify it and make it driving a relationship between pressure and altitude and temperature and altitude. The first thing I'm going to do, though, to make this problem a lot simpler is I'm going to say that for this exponent here, I'm going to just call it y. And then we can substitute it back in later. But this way, I don't have to keep writing the negative r over cv plus r, because then it's just going to get even more complicated. So the first thing we want to do is set up for integration by moving our pressure so that we have pressure on one side and position on the other side. So we have our dp over dz is going to be, so essentially we're just substituting we're putting our two equations together, and then when we do that, the temperatures from this cancel and the pressure is flipped because we're substituting it into this equation up here. So now we want to move our pressure so that we can integrate it. So we're going to end up with our dp dz equals, and we'll have negative pressure raised to this power times the mass times like the constants, and then we'll have our pressure over here raised to the y. So we'll end up with dp over dz equals negative p to the 1 plus y mg over r1 p1 to the y, like that, because this is going to be in the denominator, which looks like that. So now we can set up for integration, and what we want to do is we want to separate our constants because those are going to be on the outside of the integration. So we're going to move our pressure to the other side. We'll have negative p to the -1 minus y when we divide it to the other side, and then we'll have our negative mg over this all compared to pressure. So we'll have our dp over multiplying our dz to the other side. So this is what we have for integration. Sorry, I shouldn't have written that as fraction because we're multiplying it like that. And so this is what we get when we move the pressure to the other side, so that we can integrate with respect to pressure and position or altitude, which is what we want for this first part. And the nice thing about this is that all of these values here are just constant because we know what the initial pressure at point 1 is going to be, and then we have, the mass, gravitational constant, and RT. All of those are known values, so those can be on the outside of integration, and then we'll have this over here. So we'll have the integral of p -1 minus y dp equals negative mg over r t1 p1 to the y integral dz, like that. So after we integrate both sides, what we're going to be left with is an expression for the pressure and the altitude. And so we want to make sure we put in our limits of integration here. Initial pressure, final, initial, final. What we're left with is, I'm going to actually write over here so we have more space. From the initial pressure to final pressure, -1 over y p to the negative y equals negative mg over r t1 p to the y times, and actually I'm going to move this py up to the numerator because it's going to help in the next steps. So I'm just going to do negative y times the final position minus the initial position. Okay, so this is what we get after integration, and now the next step is we want to just simplify this a lot and move our pressure so we have everything all on one side and we have a nice clean equation. So I'm going to move this pressure to the other side, and then I'm going to raise it to the reciprocal to get rid of the power. So what we're going to end up with is the final pressure substituted in here minus the initial pressure, and then we'll still have the same thing on this side. And so the first thing I'm going to do is simplify this, and I'm going to go ahead and move the y to the other side so there's not a fraction over here. So we will have final pressure to the negative y minus initial pressure to the negative y equals pressure 1 negative y times, and the negatives will cancel, y mg over r t1 times final position minus initial position. Actually, I'm going to switch colors because it's kind of hard to see, but so this is our next equation that we get. Then what we want to do is we're going to move the pressure to the other side, and then we're going to factor it out, and so we'll be left with just the final pressure on this side. Okay, so we just moved the pressure and then factored it out like that. So now we can raise it to the reciprocal to get rid of the power on this side, and then we can substitute back the value of y. So essentially we'll just have 1 over y here, negative 1 over y here, and it's going to get rid of the powers on the pressure. Okay, so this is what happens, this is what you end up with when you raise this to the reciprocal of the y, the negative 1 over y, is that those cancel, and then we just have the power up here. So now we can bring back in our value for y and get our final equation, which is going to be final pressure equals initial pressure times 1 plus and when we put this back in, it'll flip, so we end up with CV plus R over R. Okay? So essentially, that's the solution to our relationship of pressure and altitude, using the two equations that we got, and now we can do the same thing for temperature. So yeah, this is our expression for pressure and altitude for the adiabatic reversible process of an ideal gas. So we still have to do the temperature. The temperature won't take as long though, because we already have most of the things that we need. So I'm just going to erase over here a little bit. Yeah. Just give ourselves a little bit of space to work with, but we don't need a ton. Okay, so now to relate the temperature and the altitude, we're going to start with one of the equations. We're going to start with an equation that we were deriving, but then do it for temperature instead of pressure. So over here, we're going to use this. We have our final temperature equals T initial times P1 equals initial temperature times P1 over P raised to the y. We're still going to use our y here, and this I'll just write as our final pressure. I'll make these initials since that's what I did down here. And then we're going to use our equation that we solved for earlier. I accidentally erased it, but I'll rewrite it again when we got rid of the y's over here. So we have the final pressure equals initial pressure times 1 plus y mg over, I still have a y here. So I forgot to substitute CV plus R over R into everything. So that was my bad. But let me fix it really quick. Okay, I think that looks better, right? Sorry, I forgot to put my About that. There we go. Okay. So this is our final between pressure and altitude. I forgot about the y here, so I forgot to substitute. But there we go. Okay, so let me fix this now. Actually, I'll leave the y since it's kind of annoying to write that. And so we have our y mg for RT times v final minus c initial, all raised to -1 over y. So these are the two equations we're going to use. We're just going to essentially put them together by substituting the final temperature in, substituting the final pressure into this equation. But since this is in the denominator, this whole thing is going to be flipped, and so what we're going to end up with is an equation pretty similar to this one. We will have our final temperature equals our initial temperature multiplied by 1 plus y mg over r t1 times c final minus c initial, all raised to 1 over y. Right? Or no, sorry. Just there's no exponent. Because the pressures cancel and then these exponents cancel each other out, so we're just left with this. Awesome. So then the last step is just put in the y. I'll remember to put it in all the right spots this time. Final temperature equals initial temperature times 1 minus, since it's a minus r, is going to be r mg over r t1 times final position minus initial position. Okay? So this is what we get for our... Okay? Awesome. So this is what we get relating our temperature and altitude for our adiabatic reversible process when modeled as an ideal gas. So now we can use these for our system, and if you know the temperature and the position, you can solve for the final temperature or vice versa. But essentially we have these two useful equations that allow us to relate pressure and temperature when compared to altitude.